Welcome again to Physics 371 Online. We've spent some time using Coulomb's law to define the electric field and to calculate it for a general kind of charge distribution. Now let's consider what some of the properties of these electrostatic fields might be. And we'll begin with the traditional field line diagram to give us some insight. In a field line diagram that's properly constructed, the strength of the electric field on a particular surface is proportional to the number of field lines n that are counted per unit area normal to the surface at that point. And we can express this in an equation, in a proportionality relationship like this, that E is proportional to the number of field lines per unit area on a surface. Therefore, the number of field lines passing through the surface, if we just use this equation to solve for n, is proportional to the strength of the electric field on that surface times the area. And this forms the basis for a quantitative definition of something that we call the electric flux. And the flux, as the name implies, is a measure of the flow of the field lines through a particular surface. But we quantify this by taking the integral of E dot dA, where dA is the differential area vector normal to the surface, and integrating that dot product over the surface. That tells us the flux. Now, qualitatively, we can see that this flux is related to the charge itself, whose electric field we're talking about. For example, imagine this gray closed surface within which we have two equal and opposite point charges, one positive, one negative. If we count the field lines that come out through the surface and then count the field lines that come in through the surface, we see the same number. And so as a result, the flux through that closed surface is equal to 0. Let's now consider a situation where we have opposite but unequal charges. In order for this diagram to be consistent, you'll see that there are more field lines coming out of the larger charge than there are coming back into the smaller charge, which in this case is negative. So if I count the field lines passing through that closed gray surface, there are twice as many going out as there are coming in. As a result, the flux through that surface, where the outward flux is considered positive, the flux is greater than 0. And one more that we can consider is that of a point charge through some kind of closed surface that's outside the charge. In other words, the point charge Q is not inside that closed surface. And in this case, we see that every field line that enters the surface, representing by these yellow lines, every field line going in also comes out, and therefore the flux is equal to 0 again. So these three cases give us some idea that the flux through a closed surface is related to the total charge inside the surface. On the far left and on the far right, we see closed surfaces that have 0 net charge. Therefore, they have 0 net flux. Whereas in the middle, there is a net charge on the inside that's positive, and therefore there's a net outward flux. So a quantitative statement of this rather qualitative observation is something that we call Gauss's law. So Gauss's law says that if we have a closed surface in space, the flux through that closed surface is equal to the total charge enclosed by the surface divided by the constant epsilon 0. Now let's see where that comes from by considering a special case. This is something that you may remember from Physics 142. Consider the case of a point charge around which is a closed spherical surface of radius r centered on the point charge. And we know the electric field expression for the electric field on the surface of the sphere. If the sphere has radius r, the magnitude of that electric field is a constant times the charge over r squared. And the text that I took this figure from used k to represent 1 over 4 pi epsilon 0. By definition, the flux through any surface is this integral E dot dA. For a spherical surface, the dA vector is always perpendicular to the surface, which means it's always in the radial direction, which is the same direction as the electric field vector. And so the dot product of those two vectors is very easy to evaluate because it has to be the same everywhere on the surface. The E and dA vectors are everywhere parallel. So we have EdA cosine 0, which is just the magnitudes E times dA. Now, on the surface of the sphere, we know from Coulomb's law that the magnitude of E is Q over 4 pi epsilon 0 r squared. Let's go back then to the expression for the flux. Now we have what was the integral of E dot dA is now the integral EdA. Note that I've taken the vector signs off because we're dealing now solely with magnitudes. So we plug in the expression for E and find that all of it can come outside the integral because the Q and the r squared are both constants. They're not changing as we move around on the surface. So everything comes outside and we're left with the rather trivial surface integral over the surface of dA. And I apologize, that should be a lowercase a, but I inherited this from a previous slide where I was using uppercase a. So that should be the same as the dA in the left-hand part of the equation. In any case, the integral of dA over an entire surface is simply the surface area, which is 4 pi r squared for a sphere, and we end up with this flux through the closed spherical surface being Q over epsilon 0. And that's completely consistent with the statement of Gauss's law that was on the previous slide. The result, if you think about it, does not even depend on the location of the charge inside the surface. If all the flux is really representing is how many field lines flow out through the surface, then it doesn't matter whether the charge is at the center or slightly off-center. You'll still have the same number of net field lines flowing out through the surface. So it doesn't have to be at the center of the sphere, and by the same kind of reasoning, the surface doesn't even have to be spherical, as long as it's a closed surface that has that point charge inside. So hopefully that makes sense. And that allows us to take the result that we just derived for the point charge and generalize it to the case of a point charge anywhere inside any shape of a closed surface. And by the superposition principle, then we can extend this result to a collection of point charges and even to a continuous distribution of point charges. Because remember, we calculate the electric field of a continuous distribution of charge by breaking it down into tiny infinitesimal elements. Each of those elements behaves just like a point charge. So, what we proved for a single point charge, we can make formal for the more general case of any charge distribution. That's very nice. It's a nice result. So what does Gauss's law allow us to do? And I'll just say a couple of things here. The basic idea is that the integral form, which is what I showed on the previous slide, allows us, when we have a high symmetry charge distribution, to quickly calculate the electric field in the regions around it. That's clearly going to require some examples for me to flesh out, so please take a look at your textbook, look at the examples in there, and then I'll do another example in class. But first, let's rewrite this general statement of Gauss's law in a slightly more compact form. This is the integral form, and it is the one that is most useful when you're trying to use it to solve for electric fields, for charge distributions. But it's not the most compact way. Let's consider the divergence theorem. The divergence theorem says that the integral of the divergence of a vector function E over a volume of space is equal to the flux integral of that vector function through the surface, the integral E dot dA, through the closed surface that bounds the volume. Well, that integral on the right-hand side is the same integral that appears in Gauss's law. So we can also rewrite the right-hand side of Gauss's law by realizing that the total charge enclosed by a surface, if the charge is a charge distribution rho, is simply the integral of rho d tau over the volume. So substituting both of these two expressions into the expression at the top for Gauss's law gives something very simple. We see that the left-hand side becomes the integral of the divergence function, the divergence of the function E. The right-hand side becomes the integral of rho d tau over epsilon 0, and these two volumes are the same. So if those two integrals are the same, then it must mean the integrands are the same as well. So by inference we see that the divergence of E is the charge density divided by epsilon 0. And the way I like to think about this is it's a mathematical way of telling us that the electric field corresponds to or is caused by a charge distribution. And the electric field has the property that it has a non-zero divergence because field lines begin on positive charges and end on negative charges. So this is the divergence of E written most generally. It's got the same physics and the same content as Gauss's law written in the integral form, but we call this the differential form, and it's often useful especially when we're summarizing the properties of electrostatic fields. Well, now we have the divergence. So what about the curl of E? What other kinds of properties does this electrostatic field have? In order to evaluate the curl of E, let's first consider an integral of the quantity E dot dl between 2 points in space near a point charge. So here is the picture. A point charge located at the origin of the coordinate system with field lines emanating outward in all directions, and then considering 2 points A and B and some arbitrary path that we take to go between them. So we know in spherical coordinates, which is the easiest coordinate system to use for this problem, that the electric field can be written for a point charge as Q over 4 pi epsilon 0 times r hat over r squared. And here, since the point charge is at the origin, I can use simply the regular r hat vector. It does not have to be the script r vector that we used in Coulomb's law. So we also can write down the dl vector in its most general form in spherical coordinates as having an r hat and a theta hat and a phi hat component. We first saw this when we were considering spherical coordinates for the first time. Well, in this form the dot product is trivial because only the r hat components dotted into each other give us a non-zero result. All the other terms, the r hat dot theta hat and the r hat dot phi hat terms, they go to 0. So all we're left with is that this integral is Q over 4 pi epsilon 0 times the integral from a to b of dr over r squared. And we can all do that one. The integral of that is just negative 1 over r, which then if we evaluate it between a and b gives us a negative 1 over b plus or minus a negative 1 over a. So just distributing the minus sign through, we get Q over 4 pi epsilon 0 times 1 over a minus 1 over b. The importance of this is we see that the result is path independent because a and b simply represent the distances of those 2 points away from the origin. So there's nothing in the result that tells us anything about the path that we took to get there, just where we started and where we ended. And that's very neat because if a is equal to b, we see that this integral, which now is a closed line integral, gives us 0. So integral E dot dl is equal to 0 around a closed path. That is a general property of electrostatic fields. So that's the integral form. The differential form is something that we can obtain by using Stokes Theorem. Stokes Theorem is that other fundamental theorem of vector calculus telling us that the integral of the curl of the function dotted into the dA surface vector is equal to the closed line integral of E dot dl. And so the surface over which the curl is integrated then corresponds to a particular boundary line that defines the surface, E dot dl. And so if that's equal to 0, and if it has to hold true for any surface, and that is bounded by this line integral, there's lots of different surfaces that could be bounded by this closed line integral, and so the only way that this statement can always be true is if del cross E is equal to 0. And so that's what we conclude for electrostatic fields. Del cross E is equal to 0. So just summarizing, we've determined the divergence of E and we found it's non-zero and it's related to the charge density, and we have found that the curl of E is always equal to 0. So this tells us something fundamental about electric fields. And we'll see that we've started to accumulate equations that later on we will collect and refer to as Maxwell's equations of electromagnetism. I'll see you in class.